So we're going to talk a little bit about soil temperature. As you'll notice in this graph, we've got a graph of soil temperatures in degrees Celsius. I'll make some conversions here for you in a second. But the first thing to notice is this optimum growth of these species here from about 10 degrees to 30 degrees. That's about 50 degrees to 86 degrees or so on the top end. So again, we're thinking about soil temperature here. The crops that are commonly known as cool season crops fall in that 50 to 68 degrees area, this 10 to 20 degree area of soil temperature now. So we're talking about soil temperature, not air temperature. And so it gives you a range to sort of think about, and we'll see some graphs of soil temperature in a little bit to give us an idea of what happens with soil temperatures. There's lots of other things that are happening in the soil. For instance, when we get very high on this temperature range, so when we get 90 degrees soil temperature and on up, you start to get plants that cannot function if the soil temperature is that high. So there are limits to how plants can grow based on soil temperature. The warmer soil temperature we have as we move up here, we start to do some things like sterilize the soil, and microbes aren't able to live. We have water boiling at this place. Forest fires happen way up here. Just to give you a reference, right here at 50 degrees C, we've got about 122 degrees Fahrenheit. So that gives you an idea of the range of soil temperatures that we're capable of, and really where we find ourselves when we're talking about plant growth in particular. When soil temperature, again, we need to think about what's going on particularly for plant growth and how soil temperature affects plant growth. Turns out that plants are very sensitive to soil temperatures when they grow, maybe even more sensitive to soil temperature changes than they are to air temperature changes, and they have limits to where they can grow. So you can have something like corn. We have to have 10 degrees at least in the soil to germinate. That's about 50 degrees Fahrenheit to germinate. For optimum root growth, we need to have 23 to 25 degrees C, so we're getting into the range of 70 degrees Fahrenheit for soil in order for optimum root growth. For optimum shoot growth, so the air temperature needs to be even higher than that, so mid 80s degrees Fahrenheit, 25 to 30 degrees Celsius. So it gives you an idea of the requirement of crops to actually do different aspects of their growth, from germination to full growth. This graph is a picture of that. This is turf grass. So we have turf quality, and then we have how many days they were exposed to a particular treatment. Here's the treatments right here. So if we have a dark circle, that means we have an air temperature of 20 degrees C, so that's about 68 degrees Fahrenheit, and 20 degrees C in the soil. And we have fairly steady growth throughout the duration of this experiment. But look what happens when we have the same. We have this 20 degrees air temperature, 35 degrees, so we're getting up into the 90s degrees C in the soil, and then we have this degradation of turf quality when that happens. When we have both the air temperature and the soil temperature very high, we have even more degradation. So soil temperature really matters. This here shows us that soil temperature matters much more than changing the temperature of the air. So what happens when we do this treatment here and we have 35 degrees C in the air and 20 degrees in the soil? Well, we don't have that much degradation of turf quality. So again, we can do this for every single plant that has ever existed, testing it against different kind of temperature regimes. But this is a generalization that we can make about plants, is that soil temperature really does matter. Our ability to not control soil temperature is something that we have to consider, how it is that soils actually change temperature. Here's another example of a soil that was heated. So the dark, here's our legend here. The dots as opposed to the triangles. The dots and the solid line connecting those dots shows what happens when we heat the soil to something like net nitrogen mineralized. So this is really, and then here we have the average rate of CO2 being released from the soil. So you see that, generally speaking, the heated soil has much higher activity of CO2 release. It has more mineralization of N, and those are both functions of what the microbes in the soil are actually doing. So temperature affects microbial activity. Respiration rates double for every 10 degrees C rise in temperature. So again, not only does the temperature of the soil affect plant roots, but it also affects microbial growth and respiration and what kind of activities they have in the soil. Freezing and thawing is another activity on the opposite end. So instead of warming the soil up, we're cooling it down, and we're taking the water that's in the soil and freezing it. What happens there? We can notice some real stark physical activity of the soil. So frost heaving, moving of the soil up and down. And you may have observed this if you go out if you take a look at loose soil that may have had some water in it and it's frozen overnight, it will expand upward because of the expansion of water when water freezes. In really extreme scenarios, we can have perennial plants and perennial plant roots that actually become detached. If we have a lot of water in the soil and the soil is less dense, it can actually expand a great deal. And we can have separation, as you can see here, over time. So we're moving over time, we're freezing the soil, and it's expanding and contracting. We can have just breakage of perennial plant roots in some cases, and that can be a problem depending where you are, where you're doing your production, and what kind of plants we have. On the extreme hot end, we have things like fire. And fire can change a lot of things in the soil. You notice the temperature right here. This is depth of soil, moving on this axis. The temperature is higher in that upper 7 centimeters of soil or so. Below that, it's not changed a great deal. So most of what we have happening in that top 6 or 7 centimeters of soil. You'll notice that when we do this, we know that fires do some good things, right? They rejuvenate and restore ecosystems, and they take some of this surface organic material and break it down so that so some of those nutrients become available for plants. And that's nice. That's a good function of fire. One of the other things that happen during this is depending on the organic matter in this upper horizon and the organic matter on top of the soil, we can actually have these hydrocarbons that are actually what we call hydrophobic. So they have a phobia of water, and they don't actually like to be around water. These oils and things like that are released from the organic matter can gather on the surface and actually become a deterrent to moving water into the soil. So here we have infiltration rate here. How fast are we moving water into the soil? Well, when we have a very heavy fire or even a light fire, we have less ability to infiltrate water into that soil compared to if we don't have to a situation where we don't have fire. We can move a lot more water into the soil. So it's just something to think about, again, sort of a temperature related and disturbance related. So how do soils actually warm up? The temperature is directly or sometimes indirectly dependent on 3 things. Number 1, how much energy can that soil absorb? Just absorbance, and that's really based on a factor of color and sheen of the soil. Then we have another factor that's how much energy does it take. So first is how much energy can the soil absorb. The second factor is how much does it take to raise the temperature of that soil 1 degree, for instance. So does it take a lot or does it take a little bit to raise the temperature of a given volume of soil? And then there's an energy that's required for evaporation. So if we move water from the soil up into the air, what sort of energy does that take, and where does it go? We'll do that in just a second. So soil can be dark, soil can be light, soil can have more of a sheen or brightness to it, or less, and even reflectance, or less of a sheen. And we call that term, we call that albedo. Okay, and so we can measure the ability of a soil to absorb energy in terms of this albedo of the soil. So light color soils will have albedos of 0.5, for instance. Dark color soils 0.1, and this gives us a measurement of how capable that soil is of absorbing energy. But we can have a situation where we have really dark soil. Okay, this has high organic matter in this soil. Really dark soil that might not, that though it has an albedo that allows it to absorb energy, might not absorb energy, or it might take a great deal of energy to change the temperature of that soil. Why might that be? Why would it take more energy? Well, the reasons is because we have water in the soil, and so it will cause that change to happen. Another factor could be we do have very, very dark soil, but it's covered with some kind of mulch, it's covered with residue, and that can be an influencing factor. That can be a factor where we have a barrier, an insulating barrier, as it were, that insulates this from the sunlight penetrating down actually to the soil. So we insulate that soil from change in temperature, and so having a situation like this compared to a field that didn't have that residue on it, the field without the residue would probably warm up faster than the field with the residue. So it's something we have to consider when we're thinking about timing of planting, especially in the spring, and our desire to have more organic matter in the soil. We want more organic matter in the soil. It's a good thing, but it comes at a cost, depending on how we measure it. So we mentioned that the water content of the soil is something that you have to think about in terms of how fast soil temperature changes or it doesn't. A dry soil is more easily heated than a wet one because the amount of energy required to raise the temperature of water being the important part here, by 1 degree C, is much higher than that of soil. Okay, so we have to put a lot of energy into, let's say we have to put a lot of energy into heating a cubic centimeter of water, 1 degree C. That takes a certain amount of energy. And if we compare that amount of energy with the amount of energy it took to raise a cubic centimeter of soil 1 degree C, the energy it takes for water is much more. So if we have soil without water, an air-dry soil, a soil that was fairly dry versus a soil that was fairly wet, the soil that's fairly wet would take a lot more calories being put into it in terms of sunlight energy. So it takes a lot more energy to raise the temperature of a wet soil because of the water it's in it, because the water takes a lot of energy to heat up, and subsequently a lot of energy to cool down as well. So we call this a substance-specific heat. So anything has a specific heat, right? So a desktop has a specific heat. How much energy do I have to apply to a desktop to get it to go up 1 degree in temperature? The same thing happens for water. The same thing happens for a block of lead and a block of soil. And then if we change the water content of the soil, it changes how much energy it takes to create temperature change in that soil. There's one more thing to think about. That third thing is this thing called the heat of evaporation. Heat of vaporization. It is related to evaporation. So what happens is when we evaporate water from the soil, that requires energy. That requires, and we have that here, 540 kilocalories for every kilogram of water that we evaporate off of anywhere, off of anything. It could be a pond, could be the soil. The energy comes from the sun. And when we evaporate that water off of the soil, we actually get a movement of energy, of heat energy, off of the soil. So it's just like when you are sweating, and when that water evaporates off of you, that cools you off. Why? Because the energy is leaving with the water. The heat energy is leaving with the water. So even though wet soils are hard to heat up, when they do evaporate water off themselves, they're also cooling down because of that evaporative loss as well. So that's another thing to think of as we're thinking about temperature. Look at how soil temperature changes through a soil profile over time. We can recognize some patterns. The first thing is soil in the upper horizons. So here's our 0 to 60, or even 0 to 100 centimeters here. Soils in the upper horizons tend to have much more variability. So they change more rapidly, and they change the variation with which they change is a lot wider. So you can see over the course of, let's say, a year, we have a wide space of temperature changes in the upper horizon. When we get to the lower horizon, that changes, and we have a much lower temperature swing in the lower horizons, though it does change some. We have less of a temperature swing in the lower horizon. So what typically happens, you can see in this graph, is that it takes a while for these lower horizons to actually change in temperature. So you may have heard that caves stay at a constant 55 degrees C, year round. Well, that's because they're deeper in the earth, and we don't have that temperature swing that we typically see at the surface of the earth. So in the summer, for instance, we have a cooler subsoil here. In the winter, we have a warmer subsoil. This graph here shows us. This is actually from the Powell area, the Powell, Northwest Wyoming area, and we can see that down deeper. So this purple line here, there's much less variation. It's not changing as rapidly over the course of these days, roughly a month or so. It's not changing as rapidly as these other three lines, which are farther up in the soil from 0 to 8 inches here. They are changing much more rapidly than the subsoil is, and this is part of how soils operate, is that the lower horizons don't change as rapidly as the upper horizons. So how do we control this? We can control a couple of things. We can control, like we said, soil residue, so plant residue that's on the soil. That can act as a mulch layer or reduce excess moisture, so artificial drainage comes into play here. If we drain the soil, theoretically we can heat that soil up faster than if it has a high water content there. And we also know that organic residues, organic material, can actually act as that buffer in terms of soil temperature extremes. So in this graph, what we can see is that the air temperature varies a great deal. So these dotted lines here, here's our legend right here. The dotted lines in these cases, again, have much more variability. When we have soil with mulch on it, the darker blue lines, we have less variability. These are August temperatures in this top graph. So we have much less variability with soil with mulch. If we go to January, and it's cooler typically than the air temperature during the day, soil with mulch. If we go to January, we'll see that soils are, again, they have a great variability, or air temperature has a great variability, right? It's all over the place. Whereas with soil temperatures with mulch, we have typically a warmer soil over the course of the winter with mulch, okay, versus without, and versus the air temperature. So how do we control? We can add plastic mulches to the soil. We've talked about residue. In smaller scale situations, plastic mulches can be used to actually help heat the soil up faster, depending on the color of the mulch. It'll depend on that, and give us kind of a microclimate in the soil. So that's another way we can think about changing the soil temperature to meet the needs that we might have.